Okay, now we'll turn our focus towards solving rational inequalities. These are a little bit more complex because of the vertical asymptotes that are involved, but we can still use our interval line test along with our information that we know about how these graphs look in order to find our solutions to the inequalities. We'll take some of this good advice that they give you here in the book. It says you can begin solving a rational inequality by first writing the inequality in a general form with a single rational expression on the left side and a 0 on the right. So I'm going to demonstrate how we're going to do that. First of all, we're going to take that advice. We're going to try to make sure that we make a single rational equation on the left and a 0 on the right. So that means I got to take the x plus 6 all over the 4x minus 3. I want to subtract 1 from it to be greater than or equal to 0. Now I got one side equal to 0. But I want to write this as a single rational expression, which means get a common denominator and rewrite it. So we got x plus 6 all over 4x minus 3. The only denominator that we have is 4x minus 3, so it's going to be minus 4x minus 3 all over 4x minus 3. Simply rewriting 1 as a common denominator of 4x minus 3, greater than or equal to 0. Then what we can do is we can distribute our negative. So it'll be x plus 6, then it's going to be minus the quantity, so minus 4x, and minus a negative 3, which is plus 3, all over our common denominator of 4x minus 3. Greater than or equal to 0. Next thing we want to do is collect our like terms, so we'll have a negative 3x on the top, and then we also have plus 9 all over 4x minus 3. That has to be greater than or equal to 0. So this is the first goal, is to get one side equal to 0 and get the other side written as a single rational expression. The other thing you might want to do is get it completely factored. In this case, it's not that big of a deal to get it completely factored because it's only a linear over another linear. So we only have one factor on top and bottom. Now what's different in these rational equations is when we graph these, we not only want to make sure we have when our function or our graph crosses the x-axis, and that's going to be on a rational equation. We're going to figure out where it crosses the x-axis by making sure that the denominator, or that the numerator, let me try to rewrite that again, that the numerator ends up being equal to 0. So I'm just going to go equal to 0. That's going to be our x-intercepts. So that's where it's going to equal 0. And the other thing we want to do is we want to figure out where our denominator is equal to 0, because that'll give us some more intervals in which to look for our vertical asymptote. So first thing I'm going to do is take the numerator, negative 3x plus 9, set it equal to 0. By setting it equal to 0, I'm forcing the y value equal to 0. So what we're guaranteeing is I'm going to get some location on the x-axis. So that's what those x's there represented. So I'll try to get those out of there. So to solve that, it's pretty simple. Erase too much, but let's go back here. That makes a negative 3x equal to a negative 9, which means when x is equal to a positive 3, your output will be a 0, so we know it will cross the x-axis at 3. Next thing we're going to do is we're going to take our denominator and figure out where our denominator is equal to 0, because it'll be undefined there. We'll have a vertical asymptote, so when 4x is equal to a 3, when x is equal to 3/4. So when x is a 3/4, so if this is 1, 3/4 is somewhere in this general area, we'll have a vertical asymptote. It can't be used because it's undefined at that location, so that is off limits. The other thing that might be helpful, and I kind of like looking at this, is your horizontal asymptote. It's a degree 1 over degree 1. It's a tie, so that means there's a horizontal asymptote at a negative 3/4, the ratio of the leading coefficients. So if this is negative 1, we have a horizontal asymptote at negative 3/4. So I have the relative positions in there correct. Next thing is just to get a sketch of our curve. I know it has to be approaching the end behavior of a negative 3/4. It also has to come up and cross the x-axis at a 3. It has to approach our vertical asymptote at positive infinity. The behavior by the vertical asymptote is opposite, so I'm going to come back from a negative infinity, and I have to flatten out and go towards the end behavior of our horizontal asymptote. Now, what the book is indicating here is that this, we can apply the interval line test to this. Here is one interval. If we go anywhere from 3 to positive infinity, this could be considered one of the intervals to consider the signs. The next interval is going to be between your vertical asymptote and your 0, so this is interval 2. And the last interval is out here from negative infinity up to your vertical asymptote. So this is our third interval. And we can do interval line tests if we need to verify what's going on. If our graph is sketched correctly, then I can already assume that the solutions are in this interval. We want all the solutions where it's greater than or equal to 0. Well, it's equal to 0 at 3. It's greater than only, our graph is only above 0 in this region here. So our solution should be from 3/4 all the way up to and including 3. Now, let's apply these interval line tests that they're asking us to do so we can do bigger and more complicated problems later. So if I pick a point somewhere out here in region 1 or interval 1, such as a 4, and I plug it in, all I need are the signs. So it's going to be 4 times a negative 3, which is negative 12 plus 9. That's going to be a negative number on the top. On the bottom, it's a 4 times 4, which is 16, and the 16 plus 3 is going to give us a positive, and a negative divided by positive is negative. We don't want negative values, so that's why that region or interval number 1 didn't work. If we choose a number in interval 2, such as a 2, we should find values that are positive. So if we put in a 2, a negative 3 times 2 is 6, negative 6 plus 9 is positive value of positive 3, so we know it's going to be plus over. And then it's going to be 4 times 2 is 8 minus a 3, that's a 5, so that's positive. And a positive divided by positive is positive. So that's part of our selection that we knew was going to be correct, at least from our graph. And then we can go out into the third interval and try one of those values in interval 3, which a nice easy value would be plug in a 0. If you plug in a 0, it's going to be a positive 9 all over a negative 3, and a positive divided by negative is negative. So we do not want those. So there's your first go around at using the interval line test in order to help you decide where your graph is positive or negative, and helps you solve your rational inequality. Okay, I'm going to just take a little break here because my board is not synchronized or oriented right, so I'm going to do a quick little adjustment on it, and then I'll be right back to finish this up. Hopefully that helps out a little bit. Then we'll attack question B. First thing you want to do is you want to get one side equal to 0, and then as a single rational expression. So we've got an x squared minus x minus 11 all over x minus 2. We want to subtract 3 less than or equal to 0. We have to get a common denominator. So x squared minus x minus 11 all over x minus 2. Minus, we want a common denominator to be x minus 2, which means it's going to have to be a 3 times x minus 2. So we're just rewriting 3 as a common denominator of x minus 2. Next thing we'll need to do is simplify our expression. So it's x squared minus x minus 11. I have to distribute a negative 3 here, so minus 3x plus 6, and that's all over the common denominator of x minus 2 is less than or equal to 0. And then we'll collect our like terms. X squared, and then we have a negative x minus 3x is a negative 4x. A negative 11 plus 6 is a negative 5 all over x minus 2 less than or equal to 0. Okay, now that's one of the key things that we got to be able to do. Rewrite that equation. So one side is equal to 0, and the other side is a ratio of two polynomials, so a rational equation. So take the numerator, and now, as with all rational equations, the best form to get them in are factored forms. So we'll try to factor the top, which I believe happens or occurs pretty easily. It's x minus 5, x plus 1 all over x minus 2 less than or equal to 0. Now, when you do rational equations, you want two important features. You want to know where it crosses the x-axis, and you want to know where the location of any vertical asymptotes are. So we're going to take the related zeros of the numerator, which are going to be 5, 1, 2, 3, 4, 5. It's going to cross there, and we have a related 0 at a negative 1, so it's going to cross there. X-intercepts are located. And we'll also have a vertical asymptote at the related 0 of the denominator, which is at 2. So I'll sketch in a vertical asymptote at negative 2. Then we could look at our horizontal asymptote. I guess I can look right here. It's a second degree over a first degree. So this will be an oblique asymptote, which is going to be quite a bit of work in order to find that. And it's not necessary in this problem. In order to solve this inequality, all we need to do is use these intervals that are set up by our zeros in our vertical asymptote. I don't have to have a sketch of the graph, but if you want to make one, you may. So I'm going to bypass what the graph looks like, and if you want to go back and graph it on your own, you may. But here's the different intervals that we have. I'm going to work from left to right this time. We have an interval that goes from negative infinity all the way up to a negative 1. We have another interval, so I'll call that interval 1. We have another interval from -1 all the way up to our +2, so that's going to be interval 2. We have another interval in here that goes from 2 to our 0, 5, so that's interval number 3. And then we finally have an interval out here, interval 4, which goes from 5 to infinity. If we do a sign analysis on each of those intervals, we can tell where our graph is positive or negative. So here's sign analysis at work. We're going to pick a number out here that's smaller than a -1, such as a -2. I just want to know about the signs. If I put a -2 in for x, it'll be a negative. Put in a -2 for x, that'll be negative, so it'll be negative times negative all over. I put in a -2 for x there, that'll also be a negative. So if we take a negative times a negative, it's a positive, and a positive divided by a negative is a negative. So in region 1, we're going to have negative values. So then in region 2, we're going to pick a number in between -1 and 2. I like the number 0. So if I choose 0, now I'm plugging in for every one of these x's a 0, and I'm just evaluating the signs. So that'll be a -5, so that's a negative. That'll be a +1. So it's negative times positive divided by a -2. So we're going to have a negative divided by negative, or we're positive in zone 2, or interval 2. So then we're going to go to interval 3. Now we can expect this to alternate. If we're by this vertical asymptote, I bet when we look in region or interval 3, it'll be negative. So we'll pick a number. Doesn't matter what we pick. We can pick 3, just so it's between 2 and 5. If I do a 3 minus 5, that is negative. If I do a 3 plus 1, that is positive. And then if we do a 3 minus 2, that's positive. So you got a negative divided by a positive, which is negative, just as we expected. And then we'll go out to region 4. We'll have to see what the sign analysis tells us in region 4. So we pick a number bigger than 5, which is 6. Plug in the 6 into our factored form, and that's going to give us a positive value on the first factor. There's a positive value on the second factor, and we're going to divide it by another positive in the last one. So that's a positive times positive divided by positive, which is going to give you a positive result. Okay, so now we have every interval where it gets broken up into positive and negatives. What we're interested in this one is where it's less than or equal to 0. So all we want to know is where we have some negatives. So in interval 1, so we want to include anywhere from a negative infinity all the way to -1, and we want to include a -1 because it's equal to, so square bracket there. Union, there are some more solutions here. We want to skip region 2 because in interval 2 or region 2, those were positive values, so we don't need any of these. But back in region 3, we ended up with some more negatives, so we want to include those. Now we can't put in a 2 because it's undefined, so it's going to be a parenthesis, 2, comma. We want to go all the way up to and include, since 5 is part of your solution set, to 5 square bracket. And that should be it because in region 4 they were positive. So our solutions are anywhere from -infinity to 1 inclusive, union 2 to 5 inclusive. Okay, so there's only one more example to work through on this, and that's for C. So first thing we'll do is we get one side equals 0. It really doesn't matter which side. I'm going to go 1 over x minus 1 over x plus 5. It has to be greater than 0. We worked on these the other day, getting the common denominator. Our least common denominator for this one's going to be x times x plus 5. That's your LCD. So I got to take this 1, I got to multiply it times. What I need to do is get an x plus 5 under here, so x plus 5. So it's 1 times x plus 5, or simply x plus 5. Then minus, then I got to take this 1, and I got to multiply it times. Well, I got to get another x on the bottom here to get a least common denominator, so I got to multiply it times x, both top and bottom by x. Greater than 0. So from here, what we'll have is an x plus 5 minus an x all over an x times x plus 5. And that has to be greater than 0. So if we collect our like terms, we'll have nothing but a 5 all over x times x plus 5, greater than 0. So we're looking at the two basic building blocks of our sign analysis graph, and that is where is it across the x-axis, and also where are their locations of vertical asymptotes. For this problem, there are no x-intercepts because there's no way I can make the numerator equal to 0, so we don't have any of those to worry about. But we do have to worry about the vertical asymptotes. One of those is on the y-axis. When x is equal to 0, that's a related 0 that will cause an undefined value, and also our related 0 for this one will be a -5. So at a -5, we'll have another vertical asymptote. Now this will cut it up into 1, 2, 3 different regions. And I don't need to know any other information other than that to solve this inequality. If you want to get the rest of your graph, you may. But if we pick a number out here in interval 1, such as a -6, put in a -6, that 5 is always going to be positive on the top because we can't change it. So that'll be a negative times a -6 minus or plus 5. Well, that'll be a negative. So it'll be a positive divided by another positive, which means in region 1 or in interval 1, it'll be positive. In region 2, interval 2, pick a number somewhere in here. I like the number -1. So the 5 is going to be positive. But if we put in a -1 in for x here, it'll be a negative sign. -1 plus 5, well, that's always going to give us a positive number. So we're going to have a positive divided by a negative, or in region for interval 2, we'll have a negative outcome all the time. And then on the other side is we should suspect the alternating behavior. It's going positive here, negative on that side. So what's going to happen when we get on interval 3? So kind of suspecting it might go to positive, but let's try it. If we put in a +1, we have 5, which is going to be positive, 1, which is going to be positive, over, and times another 1 plus 5, which is going to be positive, so it's positive divided by another positive, which means it'll be positive. So in region 3, it'll be positive. So we'll go back and we'll look at our inequality symbol. This says we want to find those things that are greater than 0, so that means we want to find positives. So the intervals 1 and 3 are the ones that have our solutions. So to write down our solution set, we want to go all the way from -infinity. We want to come up to, but not include the -5 because it is undefined at -5. Union that with interval 3. In interval 3, we can include 0, but it's going to be the start of it. So everything bigger than 0, all the way out to positive infinity. And that'll be our solution set for this one. So ran through 3 different graphs using the interval line test to help you do that. As you can see, I don't really need the entire graph if you want to do that. You have your graphing calculator, computer to help you do that, or you can use all the other information that we used earlier in the unit to help you sketch a graph of it. But as you can see, it's not required.